Well, the last video demonstrated the relationship of sample size to power. We were able to see that as sample size goes up, other things being equal, so also does power. So what we want to do now is look at some other factors that affect power. And I think one can safely say that along with sample size, the other factor that has a large effect on power is the size of association in the population. Other things being equal, the larger the difference, or we can say the larger the relationship between the condition in the population from which the sample is selected and the condition stated in the null, the greater the power. So, and what we're really saying here is other things being equal, when we've got a large difference or relationship in the population, we're going to have greater statistical power. So let's take a look at an example. What we're saying here is that a researcher is carrying out the same study, but in two different hypothetical populations. So we've got study 1 and we've got study 2, and the researcher is going to be comparing the effects of treatment A and treatment B. And you know, he's going to do that in study 1 and study 2. And so study 1 is carried out in one population. Let's look at the size of the relationship or difference in study 1's population. So here's our data. This is a hypothetical example. The researcher would not have data on the full population in the real world, but let's presume that these are indeed our conditions in the population. So in study 1's population, the mean for treatment A is 50, and for treatment B it's 40. The standard deviation in both groups is 10, and so we can calculate a standardized mean difference in the population. And so that standardized mean difference would compute to 1. We're dividing the difference in means by the common standard deviation of 10. So now things are the same in study 2's population, with the exception that the difference between the means is 5 points rather than 10. 50 versus 45, the standard deviations are 10, so let's calculate the size of the difference or the relationship in study 2, and it computes to 0.5 standard deviations. So we've got a larger difference in study 1's population than in study 2's population. You know, using our terminology from chapter 9, we characterize the difference of half a standard deviation as a medium-sized difference, and a difference of 1 standard deviation is clearly categorized as a large or almost very large difference. Well, okay, so then what needs to be said here is that we will have greater power in study 1 than in study 2, and that's because the size of the difference is greater in study 1. So then therefore, I mean, other things being equal, there is greater power when there is a larger difference or relationship in the population. It might be useful to consider what the power might be in a research study in which the size of association was huge. So when you have very large association, this is analogous to searching for a very big needle in your haystack. There's a big effect or a big difference that you're searching for. So here's an example of a preposterous research study. I call the research study preposterous because nobody would ever undertake such a study. The answer is so obvious before the study would begin. So suppose you were to study whether reading skills of first graders and college seniors differ. Well, obviously we've got a huge difference between these two groups. And the difference is so huge that even if we've got a lot of sampling error, even if we've got a very big haystack, it may not be a big enough haystack to prevent us from finding the needle. In other words, from picking out this very large difference. If you have a situation where there is a huge association in the population, basically a very small n will often be sufficient for rejecting the null. I mean, you've got such a big needle, you've got such a big real difference that even if you have a large n and therefore a large haystack, you may very well still be able to find that needle. Now, reduced variability in either the independent or the dependent variable often reduces power. So that let's look at two hypothetical schools of social work. And let's actually keep sample size equal. Let's say we've got 100 students in our samples, and that what we're doing is, say, follow-up study of graduates, looking to see whether obtain a social work job, yes or no, say 3 years subsequent to graduation. We want to look at the relationship of ethnicity to job attainment. In other words, we want to look at, do white students and minority students have are they differentially effective in terms of obtaining jobs? Now suppose that study 1 has a sample of 94 white students and 6 minority students. So then study 1 has very low variability with respect to ethnicity. And that's because, you know, almost everyone is in one category. 94% of students are in the white category. Now, on the other hand, in study 2, we've got a 60-40 split. 60 white students and 40 minority, percentages of 60% and 40%. So we've got really quite good and high variability here in ethnicity. We've got reasonably equal numbers in the two categories. So, and I mean, let's presume that in the population, that is to say, if we had unlimited numbers of white and minority students in study 1 and study 2, that we would have the same difference. So in other words, that we're going to basically presume that we've got the same size of association. But in which situation will we have greater statistical power? And the power of the significance test will be greater in study 2. So the message is that restricted variability in either the independent or dependent variable, other things being equal, reduces power. You know, so in study 1, ethnicity is nearly a constant. You can't study the relationship of a constant to any other variable. That's a nonsensical thing to do. A constant can never be related to some other variable. So what you've got here is a situation where in study 1 we're trying to relate a near constant to a variable, and in a situation like that power is reduced. Now next one is almost counterintuitive to the notion that reduced variability reduces power. So but the idea here is that variability from extraneous variables can reduce power. So suppose that a researcher is studying which of two treatments is more effective in reducing depression. So there may well be a treatment effect. One treatment may, in other words, be more effective than the other. But what are other variables in this situation that might affect depression levels for participants in the study? And so I've listed some here. Living situation, stressors, work, income, support systems, family, social skills, exercise, diet, sleep, health, spiritual life, discrimination, events of the day, and I suppose we could go on and make the list much, much longer. Well, if each of these variables is indeed affecting depression level, what in essence these variables are doing is they're adding extraneous variability. I mean, we're not measuring these variables, but these variables are having an effect in our experimental situation. What these variables are doing is, in essence, making our haystack larger. They're introducing additional sampling error, chance, randomness to our situation. So we're hunting for the treatment effect, that is to say the needle, that is to say whatever real difference there is, we're hunting for that situation, for that needle in a situation where the haystack has grown very large due to extraneous factors. So when extraneous variables greatly add to the variability of the dependent variable, they introduce additional randomness, they make the haystack larger, and they reduce power. What is the solution to the problem of extraneous variables? And in a way, you need to go and take a multivariate statistics course. But basically, if you include extraneous variables in the analysis, that can often increase power. So that, in other words, when you include the extraneous variable in the analysis, you control for that variable. So, and actually that does two things. One thing that it does is that it reduces sampling error. It takes out noise. It makes the haystack smaller. And by so doing, it increases power. Now, another thing that controlling for an extraneous variable can often do is reduce bias. So this brings back our study of confounding variables from Chapter 10. So it may be that your variable is a confounding variable, that it's inducing relationship, it's biasing relationship. So by controlling for it, not only do you reduce sampling error, but you also can often remove or reduce bias. I will mention that including pretest measurements in studies is a great way to increase power. In effect, by including a pretest, you control for, in this case, for instance, depression levels prior to intervention. So you're able to look at each person's change across treatment rather than just look at the scores of the different people. So, but in some pretests, in essence, control for extraneous or control variables, and they can greatly enhance your power. And though a research methods course will talk some about the pluses and the minuses of pretests, I think that most often the pluses considerably outweigh the minuses. Continuing on with factors that affect power. Use of the 0.05 level rather than the 0.01 level increases power. I mean, what happens is that the rejection regions become larger and closer to the value stated in the null. So the bottom figure shows rejection regions using the 0.05 level, and then the top figure shows the same situation. In other words, other things are equal except that the 0.01 level is used. So you can see that when the 0.05 level is used, smaller differences are going to be sufficient to reject the null. So the result was indeed in a positive direction. If we were to use the 0.05 level, a score of 104 would be sufficient to reject the null, whereas if we had gone with the more difficult 0.01 level, we would have to get out to a score of greater than 105 in order to reject. So in sum, I mean, if the null is indeed false, you're going to stand a better chance of rejecting that false null if you use the 0.05 level. In other words, your power will be greater. Now, assuming that your study sample result is in the expected direction, the use of a directional hypothesis pair, and thus a one-tailed test, increases power. And I mean, I'll state this more simply. I mean, you should not be using a one-tailed test in a situation where there isn't compelling reason to think that the result will be in a given direction. So, you know, we can take it as almost as a given, if one is using a one-tailed test, that the result will be in that expected direction. So then, therefore, the power is greater. So these examples show a situation where the alternative would be stating greater than, and the expected direction is the positive direction. And you can see that this situation, if we presume that we're using the 0.05 level in both situations, then all of the rejection region is packed in the direction that the study result is expected in. And we can trace down from about 103.3 and to see that we need a larger difference to reject if we use the two-tailed test. Use of a one-tailed test increases statistical power. The final factor that bears on power is the type of test used. And the type of test used depends on the level of measurement. So in essence, what this boils down to is the higher the level of measurement, greater the power of the test. So in particular, tests that are designed for numeric variables often have greater power than do those that are designed for categorical variables. So for instance, if you thought height was going to be related to some other variable and you wanted to carry out a significance test, your power would almost assuredly be higher if you measured height in inches, which is to say at the interval ratio level, rather than simply asked people, are you short, medium, or tall? Or on the other hand, you could also get a rank ordering of height. That would be another example of ordinal level. That would be an example of ordinal level measurement, not actually categorical data. But the best way to measure here is to measure at the highest possible level of measurement. I get numeric data, and the tests for numeric data almost always have greater power than do those for categorical data. So we've summarized the different factors that bear on statistical power. What is the standard for good power? This is tough to say. I'm going to teach you is that 0.80 is the standard for good power. In other words, we want to have an 80% chance of rejecting a false null. Basically, the higher the power, the better. But in a pragmatic sense, power can reach a point of diminishing returns. When power starts to increase, say, to a level that's really, really high, say when it goes above 99%, well, you're starting to get too much power, perhaps, or more power than you need in order to make an informed decision. Now, oftentimes, sample size is adjusted so that the researcher has good power. So the researcher basically strategizes on, well, how large of a difference do I think there is in the population? How large is the relationship that I think I'm going to find? And then uses tables or computer programs to select a sample size that's going to generate adequate power. And I will mention sometimes resources are limited, sometimes it's not possible to get a sample size that is sufficient to have power of 0.80. So sometimes you need to settle for power that's less than 80%. But in those situations, should you fail to reject the null, you know, you're not going to really know whether the situation is such that there really is no difference, no relationship in the population, or whether, on the other hand, there is indeed relationship and you just didn't have sufficient resources, that is to say, sufficient power to find it. Okay, we're looking at a power table here, and I built this power table using an online statistical power calculator developed by Length, L-E-N-T-H, and the reference is in the text. But what we've got across the top are standardized mean differences. And then down the side we have various sample sizes. And so let's take a crack, for instance, at estimating power. Well, suppose that we think that the difference in the population between the effectiveness of two treatments is 1/2 of a standard deviation. Now then, suppose that we have in our study sample sizes of 15 each. So we have total sample size of 30. Well, then what would our power be? It would be 0.26. I mean, the decimals are not shown on this table. So in other words, if indeed, let's say, treatment A was more effective in the population than treatment B, and that in the population this difference was 0.5 standard deviations, and if we had 15 people in each of our two groups, well then the probability that we'd fail to reject the null would be 74%. Our power would be 0.26. The probability that we would reject the null is that'd be our power, and we have only a 26% likelihood of rejecting the null in this situation. So that's not very good odds. We might want to, for instance, increase our sample sizes so that suppose that we continue to have this difference of 0.5 standard deviations, but now we're able to have 50 in each group for a sample size of 100. What is our power? And our power calculates to 0.70. So here we've got a 70% chance of making the correct decision and rejecting the null, and only a 30% chance of making a type 2 error, failing to reject a null that is in actuality true. Now suppose, on the other hand, that we think that the difference in our population is not 0.50 standard deviations, but we think that the treatment A exceeds treatment B by 0.65 standard deviations. Well, then what's our power, given that we continue to have 50 in each group, a sample size of 100, and now our power is gone up to 90. So this is very good power, and our probability of a type 1 error here would be down to 0.10 or 10%. Now, suppose that sample size stays the same, but that we take our standardized mean difference up to 0.80. That's in Chapter 9, our categorization for a large difference, and now power is greater than 99%, or greater than 0.99. So we sort of progressed from a difference of 0.5 to a difference to 0.65 to a difference of 0.80, holding sample size constant, and you can see as the size of the difference or association has increased in the population, our power has gone up. And then before that we came down the column for 0.50, and let's come down, and again you can see that given any given difference, so here our difference is thought to be 0.50 as we come down the column. In other words, as sample size gets larger and larger, our power increases. Now I'll just quickly mention we're presuming two-tailed tests here. If you were able to do a one-tailed test, that is, if you knew that one group was had strong reason to think they would do better than the second group, your power would be higher. Also, we're presuming that the 0.05 level is used. If you were using the 0.01 level, your power would go down. A further presumption of this table is that group sample sizes are equal. As the sample sizes get increasingly less equal, and we're going to presume now that the total sample size stays the same, as you get increasingly less equal group sizes, then your power is going to go down. This chart is pretty darn helpful for getting a feel for power. The just presented table was presenting power for the standardized mean difference. Now, this table will give you a reasonable rough estimate of power for other measures. So, as a for instance, when the standardized mean difference was set to 0.80, I mean, that's our designation of large size of association in the population. And in that situation, our power calculated to 0.79. Here's that 0.79 power when sample size is 50 and the SMD is 0.80. Now in this example, we had 100 per group and we had large association, referencing the SMD table in Chapter 9. And we had power calculate to 0.79. So what I'm trying to say to you is that were you to measure not a mean difference, but perhaps a difference in percentages, or were you to look at correlation between two variables. Though this table was designed for the standardized mean difference, you could use it to get a rough feel for power whenever you would have large size association. The power and this group size, your power is going to be reasonably close to 0.79. So then this table can be used to estimate power in different situations. Now so here's an example then. The difference in percentages, suppose that calculated to be 30%. Well, according to the chart for descriptors of size of association for difference in percentages, a difference of 30% is a large association. So in that sense, it's equivalent to an SMD of 0.80 because that's also our designation of large association. So that if you had a situation that involved two dichotomous variables, two categorical variables, and you felt that the difference in percentages would be 30%, that is to say large association, and we've got the same sample size, 50 per group, then 0.79 would be a good rough estimate of power. So the power table then could be used with different types of measures. Now, there are power calculators online. They're pretty easy to find, and you could Google search for them, and that would be a better technique than using this table, but the table is there as a reference. One final point on power is to say that the power that a researcher calculates is always a best estimate of power. So in other words, the researcher makes an educated guess about the size of relationship in the population and computes power from that estimate. Sometimes researchers will choose, say, 3 different educated guess values for the size of a difference and compute power in each of those situations. That's it for the factors that affect power, and the end of Chapter 16 has just a few summarizing points, and we'll get at those in the next video.